Mm, mhm.
My physics teachers, and I always hated when they would do this. So, for example, in my early physics class in high school,
Mm,
they would always be very strict. So, if you would say, they would ask you, "Hey, what is the answer to this?" And you would say, "Well, five." And then they would always say, "Five what? Potatoes?" You know? They
mm,
always want you to give, they are very, uptight about being extremely clear about it. Or even if you say what we talked about before with the Newton laws, like if
mhm.
you say something wrong, they were very specific about the definition. And I always say, like, why are you so uptight? And now I understand because there's so
Mm.
many misuses or misunderstandings.
Especially in physics.
Yes, especially in physics.
Yeah, maybe can you try your sharing screen?
Ah, yeah.
Okay. Oh, yeah. I can see your screen.
All right. So let us do, well, that's fine. Um, Fun with physics. All right. So, um, there are there's four Maxwell laws. How familiar are you with those actually?
Uh, I'm not much familiar really with
Okay,
Maxwell.
that's fine. That's fine. That's fine. So I'll give you my input in what I think is important to really show. I like the idea of comparing them to intuitive problems. With some
Mhm.
of them, it can be kind of hard, but you can sort of give a simplified drawing on what's happening. For example, if we take a look at the Gauss, I don't like the size. Uh, right. It's also fine. Sorry. Let's do four. So if you take a
Awesome.
look at Gauss law, which basically the Gauss law, the specific definition,
Mhm.
which as if you just write it down in one sentence, is very confusing, but actually it narrows the idea behind it down pretty precisely. So it says that the electric flux
Mhm.
penetrating a closed surface is proportional to the charge inside of that closed surface. So there's many terminologies that maybe are confusing to someone who watches this for the first time, but here the drawing really helps. So if you just give a broad definition of what is a closed surface, it's just anything. It could also be like cylindrical shape. Oh, whoops, that's not a cylinder. Cylinder, like this.
Mhm.
Doesn't really matter. Usually in textbooks, they like to use um, just a ball, and then we maybe draw a coordinate system like this, right? And this closed surface is just a hypothetical surface that exists in our plane. And inside of that closed surface resides a charge. Could
Mm.
also be several charge, but we call it Q. Now, what we kind of have to predefine before doing the PowerPoint presentation is what kind of knowledge do we assume the viewer already knows? Because maybe not many people know, so we could briefly mention this, is that a charge, always, doesn't matter if it's positively or negatively charged, emits a electric field. So if we have a positive charge, here denoted as in red, plus, always emits charge away from itself, whereas a negative charge always absorbs, like a drain. Oh, that's a nice arrow. Right, like this. And if you have two charges, they create this field like this. Right? So now we have a single charge residing inside that closed surface.
Yes.
Which I'll draw it in blue, which emits the charge outside in all directions. And we don't have negative charge. We could have, but for simplicity's purpose, we just draw one charge. And it penetrates this closed surface along. Now, we say that we've drawn 1, 2, 3, 4, 5, 6. We've drawn 6 arrows. So there's 6 electric field arrows penetrating this surface. And as I said before, the amount of penetration of electric field penetration is proportional to the charge inside. So if I have a bigger charge, let's just add another one, then this will emit more arrows outside this surface. And this is exactly what is being said. The amount, the electric field penetrating a closed surface is proportional to the charge inside of this closed surface. We can also write down the function, which is just an integral over a surface. So I have an S here. We say we are interested, E is the electric field, right? And this is equal to, what did we say? Oops. The charge inside of this surface. Now, again, we have to assume that the viewer knows what integral symbol means, what electric field actually is, what the charge is, what this weird number here is. We could potentially, we don't have to, this one needs to stay, but in very simple terms, we don't need to really go into full depths, because it's enough to say we have on the left side our electric field, which we measure on the closed surface, which is pretty intuitive if you think about the closed surface as an integral. And on the right side is what he said is proportional to, that is what equal stands for, to the charge inside. This down here is just a constant. Right? If we want to, maybe that's a little bit outside of the scope of the presentation, but we could also rewrite this whole thing as so this is the integral form, the first one. You can also write the I forgot what it's called. There's several ways to write this down, and I think that's mostly why it's confusing to people, because when you look up in the internet, what are the Maxwell formulas? There's always a different way how to write them.
Right, I agree.
And so this is not the discrete form, but the I cannot think of the name. So we take the dot product of, I don't remember what this is called in English. Of E is equal to charge density. Sorry, it's actually just our charge density. Charge density. And then there's also the phasor form. So I think we could just write the other forms down, say these are the other forms, but mainly I think this one, the first one, so phasor form would be actually almost the same like this. But I would mainly focus on the integral form because it's the most intuitive to understand.
I agree.
And you can also derive the other form. I mean, it's the same basically, but just rewritten as. Hold on, let me look up what it's called. This is annoying me that I don't know what it's called. So there's phasor form, integral form, and there it is. Differential. Thank you. Differential form. And funny thing is, there's also another law, Maxwell law, and it's almost the same. It's called Gauss law, I think of magnetism, or I think it's called magnetic
Mm.
Gauss law. So here it's actually useful if we quickly show how a magnet, let's draw a magnet really quick like this. And we sort of intuitively, if we ever had sort of high school physics, know that a magnet also has a magnetic field running from, I think, north to south pole. So if we have North Pole here, South Pole here, looks something like this.
Mm.
This is the equivalence from electric fields to magnetic fields.
Mm.
And we notice one difference, kind of, if we apply this for, oh, I'm going to delete this. We are going to do the same thing now. We have, again, a closed surface, but this time we are interested in the magnetic flux. So before we were talking about electric flux, we are talking now about magnetic flux. So how about we just throw a magnet inside of this closed surface,
Mhm.
and we know that North Pole, oh, sorry, looks something like this, right? Not really pretty drawn, but it looks something like this.
Mhm.
So what is the definition of the Gauss law? Magnetic Gauss law definition is that the magnetic flux penetrating a closed
Close,
surface
okay.
is always, what would you say?
Always proportional to the magnetic flows inside of the closed surface.
Okay, that is a very intuitive, like, yeah, it would make sense. However, now we have to add something new, and that is, it is important in these, if you look at the top one again, it is important what direction the arrows are coming from. So if we have one arrow leaving, that
Mhm.
is a net plus of
Mhm.
+1. If you have another arrow entering the closed surface, that is a net of -1. So we
Mhm.
could kind of say these two cancel each other out. So it's
Right.
very important that the penetration of a surface is dependent on the direction these arrows flow.
Mm.
So now ask the same question to you again. The magnetic flux, with this knowledge now, the magnetic flux penetrating a closed surface is always,
Zero.
so we have correct. Very nice. So we have 1, 2 leaving,
Mhm.
3 leaving. We have 1, 2, 3 entering.
Mhm.
So the magnetic flux penetrating a closed surface is always equal to 0, which kind of means that there are no magnetic monopoles.
Mm.
This is a monopole.
Mm.
It can have a source, or if it is a negative charge, it is a drain.
Mm.
Here, it's quite the opposite. And this can actually be really nicely illustrated if we look at a vector field. So this vector field belongs to the EM field. So let's say we have a positive charge sitting here, negative charge sitting here, and now we have the vector field looks something like this. Many arrows distributed, which essentially just show what I drawn before, but just for a vector field, right? Like this. But if we draw the same for a magnetic field, so we have, let's draw it as an example. If we have a sorry. So maybe we have a circuit. Here is a light bulb drawn upside down like this. And current flows from plus to minus like this. We sort of know kind of from electrical engineering class, it's called Faraday's law, that charging current, so moving charged obstacles, which is current, creates a magnetic field. So we have here our current running, and around this current that is running is a magnetic field, right? Like this. So if we assume now that we take a slice out here, like here where it's the cable runs through this plane, we draw it in here, right? Like this. So we have the perspective, this is our cable here in the middle running through, and around it is our magnetic field, like this. And this is exactly what a magnetic field looks like. So, or if we draw the vector representation, arrows run through like this. And this is what we mean by the magnetic Gauss law, which means there are no monopoles. Magnetic sources cannot be a drain or a source like in the electric. They can only go around. They don't act as a drain or as a source as the electric charges do. And that is the key point what you're trying to say when we say a magnetic flux penetrating a closed surface is always equal to zero, meaning there are no magnetic monopoles.
There are no magnetic monopoles.
Actually, there are no magnetic monopoles is the most important kind of statement.
Is this also applied to when you solve the problem? Is it very important to use?
Yes, because so let's write down the function really quick. So again, we have an integral. So we see kind of correlation, but this time we don't have electric flux. We have magnetic flux, which is denoted as H over a closed surface is always equal to, zero. There's nothing on the other side. So this kind of correlation is very important when you want to, for example, derive wave functions. So if we have electromagnetic waves, right, which are always one component electric field waves, and the other component like this, 90 degrees, is magnetic field or a magnetic wave. And they propagate into this x direction, right? So if you want to solve the easiest one would be a electromagnetic wave propagating through free space, and we want to derive the wave function for this. All these four correlations from Maxwell equations are used and very important to get the wave equation, right?
Mm.
Those are sort of applicable scenarios. So we can see that these two laws, magnetic Gauss law and Gauss law, they are kind of similar in a way. They say something different, but the way what they actually tell us is kind of similar. We have the closed surface and a field that
Mm.
penetrates that closed surface,
Mm.
right? Now, the other two laws, they are a connection between magnetic fields and electromagnetic fields. They basically state what, if one exists in a way, what happens to the other one, and
Mhm.
vice versa. So if we have a changing magnetic field, what happens to the electric field? Is there something going on with the electric field? So it gives us a connection to understand how these two kind of properties, magnetic waves, magnetic fields and electrical fields, coexist with each other.
Mm.
Um, Actually, let's start with that. Before we looked at this circuit, right?
Mhm.
And in that circuit, I already kind of said that a current running through a wire
Mm.
induces a magnetic field. And this is already kind of a correlation because moving current, or current as we before looked at, current we have here, charge. Current is a moving charge. And we have a moving charge here. So you already kind of have an idea of how these two behave. So this one is called, I will write it down as a title, is called the Ampere law and Maxwell addition. So, and for these kinds, so for the next two, there are four Maxwell laws. We covered two. And for the next two, I really would like to have a more intuitive way to explain this because I I mean, they are easy enough to understand, but
Mhm.
in a way they are kind of abstract, especially with the denotation on how it's written. I mean, these formulas here that I wrote down, they are easy enough to understand intuitively with these pictures, I would say.
Mhm.
However, the ones for the Ampere law or Ampere-Maxwell law, which is usually called, is not that intuitive. So Ampere-Maxwell law says that um, I'll just write it down. The integral along
Mhm.
a curve,
Mhm.
not a surface, closed surface, along a curve of a magnetic field,
Mhm.
dl for just line, equals to um, current, right? That's what we wrote, or that's what we kind of figured out, or what we know from
Mhm.
electricity class, which is just that I, so current, induces a magnetic field somehow along the line. This here is kind of strange to understand, but it's not really hard because, oops, because if we draw a cable that runs upwards, so our current runs through here, and we have a plane
Mhm.
where it runs through, then we say if we just take a line or a curve
Mhm.
around this line, or around, we have a curve on the surface around our current, the magnetic field that we now know runs in circles is, so this magnetic field that I just drawn here is equal to the current that runs through the cable.
Mm.
This is what the integral symbol implies.
Mm.
However, this is not complete. This is just the Ampere law. That is something that Ampere discovered, that if you have a compass
Yeah.
and let's say we have a compass here, like this, and we get closer to the cable, suddenly the compass doesn't show true north anymore. It realigns with the magnetic field that is induced by the current running through the cable.
Mm.
That is what was discovered. However, Maxwell discovered something else. Because this equation up here is not entirely complete, he added the following term. Uh, all right. This here
Mm-hmm.
is another term for the electric field.
Mm.
So before, which is a bit confusing because before we said electric field is E. If we write about, when you write it with D,
Mm.
it means E times a constant, which is called the permittivity constant. This is really mean, and this is why uh, this is why Maxwell equations are so confusing, because you can write the magnetic field as B, which is just H times permeability constant, right? So we have several terms. What do these actually mean? What is D? What is B? Well, we always assume when we talk about magnetic field or electric field that they are in free space. They are traveling through nothing,
Mm.
through a vacuum. However, they change if we have material, if
Mm.
we like wood, water, metal, and this constant
Mm.
means is the relative it's just the constant relative constant that is applied to, let's say, wood. So wood
Mm.
has a specific constant, water has a specific constant, and they change the field.
Mm.
By the way, B is measured in Tesla, famous car company, and D is measured in um, Coulomb per meter squared. But this should not really scare us. We just accept the fact now that D and E
Mm.
and B and H are kind of the same, but one of them says that it's in a specific medium, where the other just exists in free space. All right. So what do we add here? We have what do you call it in English? What is D? If we have D something dt, what is that called?
Wait a minute, I will search for it.
Like we have the inverse of integral. Like
You mean
you have
derivative?
integral,
Derivative?
derivative, thank you. So we have a derivative,
Mm.
and before we know that integral is like area below the curve, or in this case we have a surface.
Mm.
We use the surface, but what is derivative? Derivative always describes the change of
Mm.
something. So if we have plot, I mean that's analysis 101, but if we have a function like this, the derivative is just change of this curve.
Mm.
So essentially what we're saying here is that the magnetic field
Mm.
is created by I, but also this over here, which means the of um, change of an electric field.
Mm.
And the reason for that addition is if we have, again, a circuit with plus minus, and maybe we have a conductor in here,
Mm.
which essentially has an electric field, and we measure the magnetic field around here. Suddenly, in this gap in here, we supposedly shouldn't have a magnetic field, right? Because between the conductor, there is no current running. It's like, yeah, the current cannot run. Well, it fills up one plate on the other side and attracts the negative charges on the other side, but then the current stops running.
Mhm.
However, we still see, so if we draw sort of the magnitude of the magnetic field around, so like here's the magnitude going, and here it should suddenly stop, but it doesn't. It kind of maybe gets bigger,
Mhm.
then continues like this. So we still have a magnetic field between those conductors. And so as the capacitor gets charged, I think I mixed up a capacitor and a conductor. Sorry about that. Um, 1 second. Oh, okay. My roommate just slipped the notes under my door.
Mhm.
Um, so as the capacitor gets charged, it has a changing electric field in between those plates. And this also induces a magnetic field.
Mhm.
And I think for this exact topic is a bit strange or hard to understand at first. For me, it was easiest at first to just accept the fact and then think about it later on. But for this one, I really would like to have a more intuitive approach. And I think that's kind of the trade-off we have to make in this video.
Yeah, I
That,
think later
yeah,
if I listen your explanation and if I see the problem later, the most easiest and maybe that can give us intuition, it will be more easy to remember.
yeah.
Oh,
I
by the
think
way, oh yes.
I think maybe we could do a two-part video,
Mm-hmm. Oh,
and maybe it would be better to sort of, before we even go into Maxwell into
mm-hmm.
detail, it would be better to give a brief overview of the basics.
What are
Such things as, yeah,
oh, yeah, go ahead.
such things as that D and, well, let's just things as D equals to E like this, or that we just say, yeah, D is kind of the same, it's just proportional to E.
Mm-hmm. Mm-hmm.
Because the material dependency is not really important to understand Maxwell,
Mm-hmm.
but I don't want to overload the
Mm-hmm.
presentation with information that might be confusing.
I think if you can explain everything in your like this is conceptual explanation video, and
Mhm.
when we make a problem solving video, then we can really give a very simple problem that can give misunderstanding like holes in the wagon
Ah, yeah,
problem. Yeah,
yeah.
maybe we can go like that, and also uh, maybe in conceptual video after you explaining it. mm, I don't know how physics approach the um physics approach of understanding the concept. If it
Mhm.
was mathematics, then it will like go deep to one exact notation. So
Mhm.
what is I exactly and how we will define I? Do you think is it also meaningful approach to study physics, or is it just enough for your concept introduction video.
Hmm. Well, I mean, you can do that. It's more physics and maths are not the same in how they
Mm,
approach
right.
problems, in my opinion. I might be wrong, but like maths doesn't really exist. Well, it's to a certain degree made up language to describe things. And in physics, like physical equations, they are
Mm,
not true, actually, if you think about them. Like Newton,
mhm,
who said F equals ma, this equation, in a way, is not really the truth. It's
mm,
actually wrong. And like we can look at it this way. So we have a graph,
mhm,
and it's a very abstract explanation, but I hope I can make my point that way. So we have some kind of function here, and this function is the whole truth, right? So let's
mm,
say the what is it called? The function or the equation that describes everything we know, like
mm.
the world function or universe function, right?
Governing law,
No, it's called like the wait equation
governing
that
equation.
okay. So I'm looking for a term. Like theory of everything or final theory,
Oh,
ultimate theory.
yeah.
Just imagine you you know how the universe works
Mm,
exactly, and you can write down in a single equation.
mm,
So from that single equation, you could derive other equations
mhm,
like E equals mc squared, like such things. It's just you have an equation that describes how
mhm,
our universe works to exact detail.
mhm,
And let us assume that this curve, this blue curve that I just drawn, kind of represents this theory of everything, this
mhm.
function, right?
Okay.
What F equals ma is, and of course, so let's say the x-axis is what we can observe,
Mhm,
and the y-axis is just the f of observe. It doesn't matter what it is, but it's just so since we cannot observe everything, so we kind of exist from here to here.
mhm,
Like I don't mean wavelength that we can observe, but we cannot really observe atoms or what happens on a quantum mechanic level,
mhm,
but also we cannot observe what is happening outside our universe. We are very limited in what we can see.
mhm,
So this little range here is what we can observe.
mhm,
And what, let's draw it actually a little bit bigger. Let's see, this is what we can observe. And now we observe a phenomena
mhm,
like, oh, look here, there's a turning point
mhm,
that behaves a certain way. So let's make a model
mhm,
function that is way simpler, and it kind of describes the reality curve here.
mhm,
Like from here to here, it's pretty accurate. It works for what we use. And F equals ma is the exact same thing. F equals ma is not true. If you have a particle that moves